Well, this is a little follow-up video to the previous one, which was just describing the main concept of electric potential. Talked about different situations where you could measure the potential associated with some collection of charges. Now we want to look specifically at how we describe the potential due to two parallel plates of charge, what we commonly call a parallel plate capacitor. So the idea here is that charges create something in the atmosphere around them. We used to just call that the electric field. But what we're going to see is it's much more convenient to describe what's called the electric potential. It's more measurable, it's more useful to deal with, it's just an easier concept. Maybe not easier to learn because you're used to fields now, but much easier to use in practice. So each of these charges on each plate is creating its own atmosphere of potential, but the collection of them, surprisingly, creates a nice uniform potential pattern, similar to how it makes a nice uniform electric field. In fact, those two are related to each other. So if we imagine taking a test charge and moving it left or right between these plates, we described before how we change the electric potential energy associated with that system. And that potential energy is going to be due to not only the field within the plates, but also how big this test charge is in terms of its coulombs, because moving a lot of coulombs back and forth here certainly requires more work and therefore changes the energy. So let's just remind you of something that I hope this is not a new concept, but the difference in potential energy between the plates of a capacitor when you move a charge around there is equal to the amount of the charge times the field times how far you move it back and forth. Let's just call that the distance. So how are we going to describe the difference in potential? Well, the definition of the difference in potential is that we just take the potential energy and divide out the test charge, how many coulombs that is. And I didn't specify how many coulombs that was because I didn't need to. And so we get a nice expression here that the difference in potential is just the field in there times the distance through which you move in that field. That's very important to realize. You only change your potential energy and therefore your potential if you move with or against the field. Any perpendicular motion is not really important at all. And so I'm going to describe here. Sometimes you could see this described as a dot product. But I'm just going to say that that distance moved has to be somewhat at least parallel to the field. So we call this the VED equation sometimes because it's a nice acronym, delta V equals ED. What we could do with this in this situation is we could calculate how strong the field is here, because if we just algebrate this, the electric field, which remember is uniform in there, so if I know it one place, I'll know it any place. It's just the difference in potential between any two places. Oh, I wrote U like potential energy. That's just old habits dying hard there, so let's do this right. The difference in potential divided by the distance between any two places where that potential is. So let's look at a couple places here. Actually, probably the easiest is the two plates themselves. We can see that they're different by 1.5 volts, and they are separated by 3 millimeters. So we get a measure of the electric field just by dividing those. That would be equal to 1.5 volts. And dividing that by, I'm going to convert this into meters, 0.003 meters. A little bit of math there. Gives us 500 volts. And so in the common language, a scientist would say that those plates have a potential difference of, they have a difference of 1.5 volts, and the electric field then between them is 500 volts per meter. You're more familiar with the newtons per coulomb unit for electric fields, but volts per meter is actually more useful when you're relating it to the potential difference. So there's just an example of how we might find the field if we know something about the potential difference on the plates. And remember, field's very difficult to measure. I don't actually own a field measuring device, but I have dozens and dozens of different potential measuring devices. So you'll see that in your lab work as well. So I think we're going to stop here, and hopefully that's enough to give you a little audio or a visual nudge beyond what you read in your text. Anything more that you need, you come and see me or your teacher.